Perfect. Welcome again. This is our lecture 24 in high-dimensional probability and its applications to data science. This is what we're doing last class. Here's our kind of big goal. We would like to uncover interesting patterns in population, and we mathematically describe this problem using a random vector x. Just to stick to something familiar would be we have a population of people. For each person, we have D genes, and we would like to visualize the genome. We would like to see what are the patterns in the genome. So x is in D. X is a random vector. You draw a random person from the population, you look at the genome, and that's a vector. For simplicity, we will always assume that expected value is 0, and if not, we just translate everything, just subtract the expected value. The patterns, the interesting information, is hidden in the covariance matrix. Population covariance matrix of this vector is expected value of x transpose, just like the usual variance is expected value of x squared. Normally, I would subtract the mean, but the mean is already 0. Okay. The problem is we don't have access to the entire population. I can't just draw a random person from the entire population and then average. And this average, unfortunately, this one is over the entire world's population. What we do know, what we do usually have access to is a sample. A sample would be, let's say, n people. Just draw n people from the world at random, independent from the same distribution. So usually I just write this as independent copies of x. And we do this, and we compute the sample covariance matrix by averaging not over the entire population, but just over the sample. Simply take the arithmetic mean, just the usual average, the arithmetic mean of xi transpose. Okay. So the big question is, does this work? So if I run the PCA on the sample covariance matrix, will it be the same as, or approximately the same as, if I run the PCA on the entire matrix, on the entire population? And what does PCA means? We just need the eigenvalues and eigenvectors. All right, let's write it this way. Just eigenvectors of sigma n, or eigenvalues of sigma n, should be similar to eigenvectors and eigenvalues of sigma. Is this true? And when is this true? How large the sample should we take? It's a non-trivial question because we don't restrict the dimension. Dimension could be very large. And so the question is, okay, there's like 2,000 genes, and it's an exploratory data analysis. We do not know how these genes are correlated in the beginning before we take the sample. So there's 2,000 genes, let's say. How many people do we have to include in the sample? How many genomes do we need in order to uncover the patterns in the population? Is it 2,000? Is it 4,000? Is it exponential of 2,000? That'll be terrible, right? There could be a curse of high dimensionality, which says, yeah, sure, you can do it, but the sample has to be exponential in the dimension. That'll be the end of story. We can't do that. The promised goal is actually that we have just, it suffices to have a sample that's linear in size in the dimension. Okay, so if the number of genes is 2000, then well, this sample should be in the thousands, something like that. Maybe 3000, 4000, and we'll see the exact results. Okay, so how do we do this? How can we infer that eigenvalues and eigenvectors are close? It is difficult to do directly because there is no closed form expression for eigenvalues and eigenvectors. Right? For example, we know the entries of this matrix. There are just correlations, covariances. They're very simple. But how do we get from entries to eigenvectors and infer that the eigenvectors and eigenvalues are closed? There's no formula for eigenvalues and eigenvectors, and that's difficult. So we do this a little bit indirectly by saying that, by doing the following. This is our goal. We'll first approximate the entire matrix in the operator norm. And then we will use a perturbation theory that says that is true. So as long as matrices are closed in the operator norm, all the eigenvalues and eigenvectors will be closed, and therefore the PCA will also be closed. So that's our goal. Okay, good. So we're looking at this error in the operator norm between the sample covariance matrix and the population covariance matrix. And the problem is now becoming the covariance estimation problem. Covariance estimation problem. This one, which is to bound the operator norm, let's say, between the sample and the population covariance matrix. That's what we'll do today. We'll finish the entire solution of this problem today. Okay, so what's the operator norm? It's by definition almost it's something that maximizes the quadratic form V transpose matrix V over V unit vectors, and I will put it like this. This is a unit sphere. So the operator norm was actually defined as something that maximizes the quadratic. It's one of the equivalent definitions that maximizes this quadratic form. And that version of the equivalent definition is in the current homework. So you're actually proving it. Okay. All right, so we have this now. And here's a difficulty. We're taking something, it's a random variable now, over the entire sphere. That's a problem. Sphere is too large. How do we take the maximum over the entire sphere? We have to control this thing for each single vector on the sphere. So for each single vector, this is a random variable. So this is a random process indexed by the sphere. And we have to control it completely everywhere. Too many points, infinity points. So what do? We discretize the sphere. We replace it with something finite. So what do? We take the epsilon net of the sphere. And okay, remember what epsilon net is? It's a set that approximates every point to within epsilon. So every point on the sphere is within epsilon distance to some point in the net. It's something like the cell phone towers that have to be everywhere. And the cell phone towers have to be kind of an epsilon net, right? You have to be within certain distance from them. So this is our epsilon net. And we know how many cell towers can we put. So there exists an epsilon net always of size 2 over of size exponentially n. So something to the n. This was last class. The epsilon net, unfortunately, is always exponential in the dimension, so that's not a very good news for us. Because the larger the net, the more work we have to do. We have to control it everywhere. But on the other hand, we know a lot of concentration tools a lot of probability concentration tools where the probability is exponentially good, like Hovding's, Chernov's, Bernstein's, all of them are probability is good. And that would be the kind of the feeling of today's class, is that we're fighting the exponentially large net with the exponentially good probability, exponentially small probability. They should cancel each other. So that's what the idea is. Okay. Let's just choose epsilon to be a constant. I don't know, choose epsilon maybe 1/4. 1/4. So this becomes then 2/1/4. It's 8 plus 1 is 9. So 9 to the d. Should be d here. Dimension of the net. 9 to the d. Okay, so exponential net. All right. Then also last class, we showed that we could compute the operator norm on the net. So I could actually replace the sphere by the net. I'll pay a little bit of an error, but it'll be fine. And that's because the net is so tightly positioned. So last class, we showed that sigma n minus, we showed a general result for any matrix, but for this matrix, it looks like this. Okay, so the ideal would be something like this. V is now in the net. So I am replacing the sphere by the subset, by the net. And I get something smaller, but I would like it to be really tight, just like this. And we pay some factor that depends on epsilon. Not large, just a little bit. In this form, this result will be the homework. We did a kind of very similar form of this, but not exactly this one. Okay, good. All right, so what is this? Epsilon is 1/4. So 1 minus 2 times 1/4 is 1. So we'll get 2 times the maximum of V. And all right, let's just think. What is this? It's let's say V transpose sigma V. What's this? Let's just do it in one step. We did it last time, but let's do it today. V transpose sigma V. What is that? I put V transpose here, sigma V, and I get 2 copies of inner product between X and V. 1 copy, another copy. Yeah, okay, are you lost? No, okay, let me do it here. V transpose sigma V is expected value. You can pull it out. V transpose X, X transpose V. So this and this are both inner products. So it's XV squared. Okay, so that will be XV squared. So it will be here, it would be expected value of XV squared. And the first term with the empirical covariance matrix will be similar, except the expectation will be over the sample, which is 1/n from 1 to n, XIV squared. So one is the empirical average, the other is true average, and that's it. And we would like to estimate it now. That was what we finished last class. Okay, any questions? Okay, cool. So look, this is this thing is a random variable for a given V. It's a random variable because it depends on the sample. We draw the sample, we do this as a number, so it's S of V. So what we're looking at here is a random process. A random process indexed by points in the net. But now, very fortunately for us, and we did a lot of work for it, it's not indexed by the sphere, which would be the continuous, would have a hard time trying to locate the maximum. But it is indexed by a finite set. So it's just a maximum over finitely many points. Oh, sorry, over finitely many random variables. And that we could do by the union bound. So our first step here would be to to control S of V. Something like this. That we wouldn't like to say that S of V cannot be too large, larger than, I don't know, something like this. To show that the S of V is small for each fixed V. And then we'll take the union bound. And that's okay, that we could do, because S of V is just a sum of independent random variables. Right? For each V, it's a sum of IID, independent and identically distributed random variables. And for that, we do have tools. We have Chernoff, we have Höfding, we have Bernstein. We are well equipped to do that. And let's decide which one we apply here. Okay, it can be Chernoff, because Chernoff applies for Bernoulli random variables, for 0 ones, and this is not, these are not 0 ones. It could be Höfding. Höfding applies for Gaussian normal random variables or sub-Gaussian random variables. But it can be Höfding. Why? Why we can't apply it for an unequal sum of the concentration for the sum for sub-Gaussian random variables? Why does it not apply here? That'll be ideal, actually.
Because we have square.
Pablo, you're either muted or you don't.
Because we have a square there.
I can't hear you. I don't know. Or maybe I'm muted. I'm sorry. Can you say it again?
Can you hear me?
Yes, yeah, I can hear you now. I was.
Oh.
Yeah. Okay.
I suggested that the problem is the square with.
Yeah. Exactly. Even if xi in the ideal case, like xi's are normal. Let's say, so xiv's are normal. Now we have normal squared, and the normal squared is not sub-Gaussian. Right? Gaussian is but the Gaussian square is actually sub-exponential. It has heavier tails. So what? So fine. We did have Bernstein's inequality specifically for that purpose, and actually this was the purpose that we did it before. So that's fine. We will use Bernstein's inequality. For sub-exponential random variables. And I'll remind it, of course, right now. So this is what we'll do today. So theorem, Bernstein's inequality. And this is from lecture 14, October 3. We look at the sum of independent sub-exponential random variables. And what does that exactly mean? Let me remind this. So it means that the tails, just like this, the tail of xi's is something like e to the minus. For sub-Gaussian, the tails would be something like this. Don't write this yet. E to the minus t squared times a constant. That will be sub-Gaussian. Sub-exponential tail is heavier. It's just e to the minus t. And there is maybe some constant. And the smallest m here is called the sub, up to a constant, is called the sub exponential norm. It's actually a norm. So we did this last time. Okay, so we have sub-exponential random variables. And then we're looking at their sum. I'll subtract the expected value here like this, greater than t. So this is the tail. I want this to be small. I don't want this to be large. So small probability 2e. Now, in the ideal world, the tails are sub-Gaussian because it's a central limit theorem. So something like t squared over sigma squared, where sigma is a variance, something like this. This will be totally ideal. But they can't be because sub-exponential tail, even for one random variable, the sub-exponential tail is already heavier than sub-Gaussian. How can I have e to the minus t squared if I don't have it even for one random variable? Of course I can. So there will be a mixture of two tails. will be one good tail, which is sub-Gaussian. And the other tail would be sub-exponential, T over K. So sigma is kind of is a variance proxy. I would like to write here some variance, sum of variances, which with variance of the sum, but I can't. And that actually the variance proxy is this, just sum the norms squared, and K is the largest of them. Sorry, guys, it's a little technical, but the idea is that if you have sub-exponential run the variables, then there's some becomes a mixture between Gaussian and sub-exponential. So central limit theorem cooks up somewhere. It's kind of it lurks in the background, and it manifests itself in this tail. So they want to be normal because of the central limit theorem, but they can't because they're individually sub-exponential, and so that's a correction. Okay, so that's what we did. Okay, let's prepare this theorem for our specific applications. We have sum divided by n, and they are all identically distributed. Okay, so let's simplify the sub-Gaussian. They're all xi's are identically distributed. And so sigma squared, this one, is just a sum of, no, all these norms are the same because of the identical distribution. And so sigma squared is the same as k, which is our maximum. It's k squared n. And k is just one of them, I guess, x, say 1. Okay, so I would like to have the probability of 1 over n, that's a new factor, 1 over n, minus expected value is greater than, let's say, delta. Okay, how do we create 1 over n? I will move n to the other side, and now apply this for t, that's delta n. Okay, correct me if I'm wrong. I'm just doing this basic arithmetic to create this prefactor 1 over n that we have here. Okay, so I would like Bernstein's inequality to have that factor too. And I'm creating it by, let's say, if I move n to the other side, I apply Bernstein's inequality for t, which is delta n, of course. Okay, so yeah, I get C.
But here, xi's are actually the inner products of xi and v.
Oh,
right?
Yeah. That's a bad notation. Yeah. Yeah, you're right. It's a bad notation. Just imagine their xi's will actually be the inner products. I should have written zi's or something like this to avoid this colliding. Yeah. Yeah, minimum of okay, let's see, t squared. So t squared is delta squared n squared over, and sigma squared is k squared n. And what? And t is delta n divided by k. Okay, I think one copy of n cancels here. And we get minus c times the minimum of delta square over k squared, delta over k, and n is a common factor. Okay, whatever. Okay, so this is a version of we just proved the version or deduced the version of Bernstein's inequality for normalized sums for averages. It's a mess a little bit, but what's important here is that the probability becomes exponentially small in n. So if I increase the sample, the probability is getting exponentially small in the size of the sample. Don't look at this. This will be just constant later. All of these deltas and k's and c's, they're just absolute constant. So technically, this will be like 2e to the minus n, basically, and that's great. That will be what would allow us to beat the cardinality of the net, which is 9 to the d, and we will beat this with e to the minus n. And the idea is that n has to be just linear in d. So to do that. So that's the idea of what will happen next. Okay, cool. Now we have all the tools, and we can finally state and prove the theorem that we're doing is a theorem about covariance estimation. If let's do a simple version of it first. Let's say all of them are normal. Mean zero, variance sigma. And n is a linear sample, so it's just enough to have larger than a constant times d. Then covariance estimation is possible. Let's say 0.1 times sigma. Or with probability, this is a random thing, with probability, with high probability. With probability at least exponential in the size of the sample. So with huge, extreme certainty. So it's a relative error. I'm saying that by increasing the size of the sample, but just linearly in the dimension, we can always achieve relative error, let's say 10%, and we can do any error here. From the proof, it will be clear how to make any error. But let's prove the simple version. Okay, guys, everything clear here? So we have the tools now. The most important tools are the small epsilon net, the bound on the epsilon net, which is exponential in the dimension. The bound on the probability, which is exponentially good, but e to the minus in the size of the sample. And now we combine them together, and it will beautifully produce the covariance estimation theorem. Okay, anything that we need to discuss before we go to the proof? But the proof is just a few lines of combination of this. Yeah. Okay, perfect. Okay, so we are proving the theorem for normal distribution just for simplicity. And maybe the homework will be clear from the proof that the normal is actually not needed there. But just okay. Proof. First of all, just without loss of generality, WLOG, let's assume that the operator norm is 1. So we don't have to carry it over too many times. If it's not 1, then divide both sides by that norm. If it's 10, for example, divide both sides by 10, just rescale our distribution. Let's say shrink x by the factor, I think it will be root 10 actually. And then we can do that. So y. Just mark it for you, just to think about why. Okay, so 3 steps. First, we fix any vector on the sphere right here. So we fix actually on the net, we fix a vector on the net and bound this thing using Bernstein's inequality. All right, so x was, all right, let's think. So x is normal with mean 0 variance sigma. So xv is still normal. Is normal with mean 0 and variance, and we don't know what variance is actually. So xv is normal with mean 0 and variance sigma squared that we will compute right now. But it is clear that it is normal. Yeah, we have a normal random vector, and this is a linear transformation of it. So think of what is it's like in coordinates. It's sum of xi's vi's, and xi's are normal, and the sum of it's a weighted sum of the normals. It's always normal. So it's clearly mean zero, but what's the variance? Let's see, the variance is expected value of x v squared. And we did this exercise so many times. V transpose expected value of x, x transpose v. I'll do it in one step now. This is v transpose sigma v. So that's the variance. Yeah. Okay. Are you with me, guys? I'm not losing you. If I'm going too fast on this, just let me know. V. And this is bounded by the norm, the operator norm. Right? Just think what operator norm is. Operator norm actually maximizes the quadratic form over the all vectors. So it's definitely smaller than that, which we assume to be 1. Perfect. Okay, so what's the result? XV is normal with mean 0 and variance at most 1. Great. Normal with mean variance 0, mean 0, variance at most 1. So it's sub-Gaussian, definitely, right? So we have this sub-Gaussian tail minus t squared over sigma squared. It's a sub-Gaussian tail that holds for the normal distribution with variance sigma, and sigma is less than 1, so this is further less. I can just drop sigma basically to t squared. Good. Okay, so what are we doing again? Let's remember, we're trying to bound this thing. We said that each norm, each inner product xiv is sub-Gaussian with mean 0, variance at most 1. Perfect. Now let's square it. Well, when we square it, let's square both sides actually. So xv squared less than s equals, okay, so this would be, I think we just change the variable. We change the variable and let t be s be equals to t squared, I think. We get less than 2e to the minus s. For any s. And just change variables, introduce that. And that means that this is sub-exponential. The square is sub-exponential. Perfect. Not a big surprise, of course. The random variable is sub-Gaussian, the square root is sub-exponential, and the sub-exponential norm is bounded by a constant. And that's because the sub-exponential norm is, let me show you this. Sub-exponential norm is the smallest m here, so we don't even have any m. It's just a constant. Perfect. Okay, so at this point, what do we have? We have this sum that we want to bound. Each term in this sum, the square of the inner product, is a sub-exponential random variable with this k will be just a constant. Okay, so we can just forget about k. Perfect. So let's apply Bernstein. Almost there. So apply Bernstein. Inequality. In fact, we will apply this form of Bernstein's inequality. We prepared. Apply Bernstein's inequality for yeah, bad notation, I know. Instead of xi, we apply it for xiv squared. K is a constant. It's a Gaussian norm. We decided it's a constant. And delta, let me think, delta. I don't know. Let's try. Let's try like 100, 0.01 n, something like this. No, just 0.1. Yeah. Yeah, 0.1. Okay, let's do it. So we have probability of the sum 1/n, the sum xiv squared minus expected value of xv squared. I'm literally applying this now. It's greater than 0.01. It's less than 2e to the minus. And then a miracle happens, and we're very happy because delta is 0.001. It's a constant. Delta square is that too. K is a constant. So all, and C is a constant. So all of this becomes a big constant, small constant. So like maybe C1 times n. Yeah, okay, that's what we worked for. We wanted to bound each S of V, each this thing, each error that depends on V. And we bounded. We said it's with very high probability, it's less than 0.01. So the error is extremely good with extremely high certainty. Perfect. So remember, this was S of V. We're almost done. Now it's easy to take the maximum. Remember, we have to take the maximum here over the net, but the net is small. Kind of small, I don't know, compared to the probabilities that we're getting. So let's take the maximum over the net. S of V is 0.01. So we're running the union bound here. What is it that what is this event? The maximum is larger than something. So it means that there exists some V for which S of V is larger than something. So we're looking at the union of events here. It's a probability of the union of these bad events. And this is less than the number of these events. And we took in the probability of the union. So it's less than the number of events times the probability of each. Times the probability of each. And probability of each is 2 to the e minus c1n. It's just a union bound. Yeah, everything is good, people. Yeah, not lost you yet. Okay, I will not lose you again because we're almost done. Then the net, we know it's small. It's 9 to the d, and that is from here. It's 9 to the d, and we're almost done. So this is what this is. 2. It's like 9 to the d times e to the minus c1n. So I would like it to be minus, let's say, c1n half over half, something like that. So this is true if we assume that n is larger than cd, where c is some large constant. Yeah, see what's going on here is there's exponential in d is fighting with exponential in n. And so if I assume that n is like larger than 1000 times d, it will sort of, n will win. So n wins and we're done. So this means that this event, the bad event, the large deviation event, holds with very small probability. So its complement to this event holds with extremely high probability, 1 minus 2e c1n over 2. And when it holds, the operator norm is less than 2 times the maximum over the net. that is from here. Let me show you very quickly here. That's from here. The operator norm was bounded by 2 times the maximum over the net. And the event holds, so this is less than 2 times 0, 0, 1, which is less than 0, 1. So that's what we need. QED. We've proved the result. Yay! That was a non-trivial theorem. I don't know when it was proved, but certainly not before 2000s or something like that. That a sample linear in size in the dimension suffices for covariance estimation, regardless of the distribution. I mean, the covariances, they could be anything there. We don't know what happens inside the data. We don't have to look at the data. This is a worst case scenario.
But this also happens with operator norm, which means, as far as I remember, we said that it's equivalent to the comparison of the largest eigenvalue. Right?
Yeah. Yeah, we'll do that now. We'll make that conclusion now. So we established, let's see. So we established this step. So sigma n and sigma, they are close in the operator norm. We're able to estimate them in the operator norm. And what we'll do next is we will say that this implies that the eigenvectors and eigenvalues are close, and therefore the PCA works. So this link we haven't made yet, but we'll do it now. And this link is based on perturbation theory. This is a very general step that says that if the two matrices are close in the operator norm, and that's why we did it in the operator norm, then their eigenvalues and eigenvectors are close. So yeah, so what we want is that this, which we already know, implies that the eigenvectors and eigenvalues are close. These are eigenvalues, and these are eigenvectors. And this is a question mark. This is what we're doing now. And this is already check mark. That's what we have. Okay, so that's based on perturbation theory. This is very general, and you probably should all know it, regardless of whether you work in probability or other fields. Weyl's inequality, for example. It just says that that is true for eigenvalues always. For any two symmetric matrices, A and B, if you compare their eigenvalues, the worst error that could be is the operator norm, A minus B. We'll not prove it, it's a linear algebra thing, but that's one of the results that says eigenvalues are fine. And this is the reason why we worked with the operator norm. Okay, good. So that's Weyl's inequality. This is for eigenvalues. So eigenvalues are okay, they're fine. Now, what about eigenvectors? They're also fine. But there are two disclaimers. First of all, the eigenvectors, they're not, first of all, we have to, they're defined up to the scaling. Let's say if V is an eigenvector, then 10 times V is an eigenvector. So in order to compare them fairly, we have to normalize them. There should be unit eigenvectors. That's one thing. Even if we normalize them, the eigenvectors are still defined up to sign. So if V is a unit eigenvector, then minus V is also a unit eigenvector. So we have to account for that too. Yeah, we have to account for that too. And third, and most importantly, imagine what happens if we have the two eigenvalues, let's say lambda1 and lambda2, that are very, very close, almost identical, but lambda1 is slightly above lambda2. Then we have corresponding eigenvectors. Okay, fine. But now, suppose I make a very tiny perturbation, and that tiny perturbation could swap the order between lambda1 and lambda2. Right? Now lambda1 becomes smaller and lambda2 slightly larger. What effect does it have on the eigenvectors? The eigenvectors also swap. And that's bad, because eigenvectors are actually perpendicular to each other. So it was this situation, and now they swap completely. And now how can I compare the eigenvector that was this to eigenvector that's this? That's impossible. So eigenvectors are actually unstable because of the ordering.
But as a set, they are kind of stable as a set, but we don't know.
Mm-hmm. Exactly. As a set, they are stable, but as a actually no. So as a complete set, they're maybe stable. But we're looking at the top eigenvectors. So I'm looking at the first two eigenvectors. Let's say looking at the first two eigenvectors, and suppose the second and third eigenvalue are very close. Then I can a tiny perturbation will change the second eigenvector to the third eigenvector, which is perpendicular. And so my plane, that the span of the first two will suddenly be very different. Okay, so the set of the first two eigenvectors is actually unstable. Is it clear? Yeah, just because of the ordering problem. Okay, so to make it stable, we need to assume an eigenvalue gap or spectral gap, which basically says that, okay, we want the second eigenvalue and third eigenvalue to be different, very different. We want some gap between them to avoid this problem. So yes, they're okay. Assuming the spectral gap. Otherwise, if let's say the kth eigenvalue and the k plus 1th eigenvalue, the next one, are very similar, a tiny perturbation can swap the eigenvectors. And they are orthogonal. So the swap will be a huge change. The plane will suddenly become orthogonal. So that's not good. But if we do assume eigengap, then everything is good. And this is how we assume it. This is called Davis-Kahan. Davis-Kahan inequality. There are many forms of it, and I will show you one of them. For any d by d symmetric matrices, A and B. Just let's think, what do we need for PCA? We need to project on the top eigenvectors, right? So let's state it in this form. So let PA be the orthogonal projection onto the span of the first, let's say, k eigenvectors of A. And PB will be the same thing, orthogonal projection onto the span of the top eigenvectors of B. Then the projections are close in this sense, in the operator norm. These projections are close, they're less than the norm of A minus B, which is good, divided by the spectral gap. So this is the first k eigenvalues, and then I would like to have a gap between them and the rest of the eigenvalues. I would like them to be separated in order to avoid the swapping situation. Good. Okay, that's it. We don't have to do any more work. We just say we combine this. Now we just combine this theorem that says that if the sample is linear in the dimension at least, then the operator norm is fine. The two matrices are close in the operator norm. If they're close in the operator norm, now A is my sigma n and B is sigma, then the eigenvalues are close automatically. And eigenvectors are also close, provided that there is a separation, a little bit of separation. So the summary is that the PCA is meaningful. The PCA works. So the PCA with, let's say, k top eigenvectors on the sample is similar to the performances, is guaranteed to be similar to the PCA on the population. And we'll see all the patterns in the population from the sample, as long as first the sample size n is at least linear in dimension, in the number of parameters, number of dimensions, d, and b is there is an eigengap or spectral gap. The top k eigenvalues of sigma of the population covariance matrix are separated, a little bit separated from the rest of the spectrum. And we can observe that on the sample, if that's true or not. And if not, that's fine. If not, then we can just, if not, that means that the kth eigenvalue and the k plus 1 is very close, and it means that maybe we should include maybe k plus 1 too. Maybe there's some meaningful information in that.
Yeah, it's actually, I think for PCA, when in practice you select which dimension to select for PCA, one of the suggested criteria is to look for this gap, right? To exactly cut off there. Exactly.
So you look at how do you run the PCA in practice. If you look at the eigenvectors and how they decay, and you look at this gap, that's maybe a meaningful indication that the useful information is here, and this is just a junk. You just cut it off there. Yeah, so that's the end of the theoretical story. It's really convincing theory. It's very, very good theoretical backing, unlike the, let's say, the other visualization methods. And you can run that. You can run PCA with these guarantees. We can make it kernelized. So instead of the usual distance, we can map them. We can use kernels, and that's also very useful. We'll talk about that a little bit later. And here's how it works. Let me show you how it works. But any questions about this theory? Yeah. Good. Good. All right. Well, we've seen some pictures how it works, but this is, yeah, for example, this one. This one is a single cell data. It's an idealized version of that, very, very cleaned from some paper of Braccio 2020. Genetic data also. This is an idealized version. There are some clusters, maybe 3 clusters in this data, and we run the PCA. We looked at the eigenvalues of this. There are top eigenvalues 1, 2, and 3, which may correspond to the clusters in the data. So 1, 2, 3 clusters, and there is eigengap here, and then there's a bulk of eigenvalues there. This blue points is my illustration of this. Really, there's thousands of, maybe hundreds of points here. So there are really like 3 separated, and then there is a lot, like a bulk, a lot of eigenvalues here. Then they suddenly stop there, which is surprising. And then there is one here. So that's what in the ideal situation in practice, that what looks like. We have isolated eigenvalues and they look like outliers, but in fact, they are, these outliers is where all the information is. They serve as a signal for us, the true information. They signal the structure of the data. This is where you would like to project them. And the rest eigenvalues is a bulk of eigenvalues, which serves as a noise. So it's like noise and a signal. And we would like to isolate the signal by PCA. Good.
So does that mean that like for choosing a K for PCI, we just want to like plot the gaps between eigenvalues and choose the first K with greatest gaps from others? So how it works?
Can you say it one more time? I didn't catch the beginning of the phrase.
Yeah, so it's kind of a method to choose K for the PCA. We can plot the eigenvalues and choose the K which like have the gap from others.
Yes, yeah, that's a heuristic suggestion in practice, is that look at the eigenvalues, and ideally there are some isolated ones and there is a gap, and then there is a lot of them here. And so these lots of them probably is just a junk. And the ones that are separated, these are the interesting ones. So you run the PCA, stop here. So just take this for K. In this case, K is 3, maybe 2. Yes, exactly. So that's a suggestion. But it's too good to be true, right? It rarely happens that we have such a clean data that we have like 3 here and the rest is just, and there is an eigengap and the rest is a bulk. And so what will happen next is we will try to understand what happens in practice actually. What if this is not true? And for that, the first question is, the first question we may ask ourselves is, what is even bulk? Like how do we distinguish the bulk, the noise here, from the signal? When I plotted this picture, you see how I plotted the histogram. There's this blue thing here, the blue bars. They are the histogram of the eigenvalues. There are how many each bar represents how many eigenvalues fall into this very tiny interval. So in this histogram, you see that the bulk eigenvalues, how are they distributed? They are not distributed uniformly in here. There are more eigenvalues here, for example, than here, because the histogram is higher. So there is some very strange distribution of the noise here. And in order for us to understand where the noise is and where the signal is, we should understand what's the shape of the noise. That's our null model, right? If we see something like that, it's a null model, and then we just chop it off and look at the rest of the signal. And by the way, it's pretty beautiful. It should be total junk. Maybe it should be normally distributed, and maybe it should be uniformly distributed. Here, the eigenvalues should be everywhere because it's junk, but they're not. It's like this. I just fitted the curve here, which is crazy. What is this even? So to understand what that is, what this noise is, I made an experiment. I said, okay, this question is about noise. So let's take out the clusters. Let's look at the data that is purely white noise. And for this, my distribution will be just a normal distribution, standard normal distribution. So let's take the standard normal distribution. It's a pure white noise. So the normal random vector is completely isotropic. All directions are possible. And I take the sample. So I take the sample. There are just points in the space. There are no information in them, no clusters, nothing, just pure noise. And let's plot the eigenvalues of the sample covariance matrix. Now, the true covariance matrix is, of course, identity. That's why it's here. The true covariance matrix identity, but the sample covariance matrix from these points is not identity because of the fluctuations. And so there are eigenvalues. So let's look at that. Let's look at these eigenvalues. So here's a couple of experiments that I made. This one is 1,000. I took 1,000 points in dimension 6,000. And here's what we see. So this, of course, there is no signal now. There are no points that that are here because there are no clusters, there is no information, it's pure white noise. But there is a lot of eigenvalues right there. And the eigenvectors, again, eigenvalues, again, they're not uniformly distributed, but that is interesting. So they're not uniformly distributed, which would, in which case the histogram would be like that. They're not normally distributed, in which case a histogram will be like that. They're distributed like this. And I made another experiment. I played with different sample size and different dimensions. This is sample size in 1,000 in dimension 2,000. So the oversampling rate is 2,000. And again, there's something like this. Very cool, mysterious curve. And I took 1,000 dimensions in dimension 1,000. So there is no oversampling, the same numbers, dimensions. And there is, it looks like there is an infinite singularity, and then there is like this, and then there's like that. Okay. And then I made an opposite example where the dimension is actually very huge, I think. Yeah, and then there is almost like this, almost like a semicircle or something like this, ellipse. Yeah. So this mystery, which comes out of nowhere, there is no signal there, it's just pure white noise. This mystery was actually studied, yeah, and that was what we'll do next in the next two classes. We'll try to demystify this phenomenon, the eigenvalues of a completely random sample covariance matrix 1 over n xi transpose covariance matrix of a completely disordered data, very noisy. Let's say just pure noise in dimension d. Here it should be d. The eigenvalue distribution is actually a different distribution from what you've ever seen. It's not normal, it's not Poisson, it's not geometric, it's not exponential, it's nothing, not uniform, it's nothing like that. It's a new distribution that's called Marchenko-Pastur. Marchenko-Pastur distribution. Marchenko and Pastur are both Ukrainian mathematicians who discovered this phenomenon in about 1967, and it became one of the best studies phenomenon in random matrix theory. And we'll actually discover it ourselves, and we'll prove it. What is it? And that would help us in practice. Actually, it does help people to distinguish between the noise and the signal. So let's say if I see something like, let me see, if I see something like this, something like that. Oh, let me do it one more time. If I see a histogram of eigenvalues that follows like this, maybe, then I would say, okay, now I know this is noise because it follows Marchenko-Pastur, because I fit Marchenko-Pastur to that. And this must be signal. So this must be the interesting part. And that is where I should run PCA. This should be the K. But in order for us to do that, we need to understand what noise is so that we can take it away and effectively denoise the noisy data. So that's a modern approach to denoise the data. But we'll do it next time. And next time is not this Friday, but Monday. I'm done. Any questions? Any questions about this, about anything related? Okay, good, guys. All right, I'll stay. And as usual, we meet with one person who is here, just to chat, just informal. I would like to just to get to know you better. And maybe Kate Безвербна, can you stay after talk?
Yes.
Yep, perfect. Хорошо. Добре, ми з вами туди побачимося. And everybody else, if you have any questions or any suggestions, let me know.
No, I have a question about homework.
Yes, Dmitry, let's do it now. Yeah.
It's about formulation in problem 2, part C.
Problem 2, part C. Yes, there is a typo. It should be for formula, obviously in B. May fail.
In B.
Yeah. I'll correct that. Yeah, sorry about that. There is a little typo, which from the context, it's clear that it should refer to B, because B is for. Oh no, it's not actually clear from context, because there's A and B too. B, yeah, B. Yes, thank you. Anything else? Yeah, bye, Daniel. Okay, all right, bye, people. And Kate, stay here, and everybody else, we'll see you on Monday then.
Yeah, thanks, bye.
Bye-bye.
I have one question.
Yes, Alexander.
But can you stop recording because it's?
Oh, yeah, I forgot. Yeah. Of course.